Hello everyone, welcome to Probability and Statistics for Data Science. Today we're going to talk about the probability mass function, which is the user interface of discrete random variables. In the overview on discrete random variables, we made the analogy that a random variable is kind of like a car, in the sense that a car has a very complicated motor, but we don't need to even be aware of the motor or know anything about it to actually use the car. We just drive it with the steering wheel. In the same way, random variables have a rather complicated definition in terms of probability spaces, but we don't really need to be aware of the probability space to use the random variable or to estimate it from data. Instead, we use the probability mass function, which is like the user interface in that sense of the random variable, or the steering wheel in our analogy. So let's get to it. We're going to talk about the probability mass function. Ultimately, our goal is to model quantities that are discrete. Some examples include the number of students attending a class, the number of goals scored in a soccer game, or the number of earthquakes occurring over a year. We model such quantities as discrete random variables. In our notation, deterministic variables that have a fixed value, we just write them normally. Well, that was a thick line. In contrast, random variables that are uncertain are written with this tilde, with this squiggly line on top. We never say the random variable is equal to 3. We need to talk about random variables probabilistically because they have several possible values. This is the whole point. They're uncertain. So we say the probability that the random variable is equal to 3 is 0.5, for example. And the probability mass function actually encodes these probabilities. Okay, so what is a random variable? We've been over this in a couple of videos, but let's just remember very briefly. If you ask a mathematician, if you ask a data scientist first, they'll tell you, well, it's just an uncertain variable that I include in my model. It's described by certain probabilities that are estimated from data. However, if you ask a mathematician, they'll tell you it's a function mapping from a probability space to the real numbers. And we already reconciled these two definitions. They're equivalent in some sense because it follows from the properties that we derive from this definition that the random variable is in fact completely characterized by its probability mass function, so we can operate with it in the way the data scientist is saying. Today we're going to focus on that, on the data scientist's point of view. Connecting to that, the probability mass function encodes all the probabilities associated to a random variable, a discrete random variable. It gives us the probability that the random variable is equal to each of its possible values. Remember that the set of possible values are called the range of the random variable. This is the mathematical definition. It's a probability of this event in the probability space that maps to a particular value. But again, we're not going to obsess about the mathematical definition in this video. We often say that the random variable is distributed according to the probability mass function because the probability mass function completely characterizes the behavior of the random variable. Okay, so we derived these properties in the video on the mathematical definition of discrete random variables, but let's remind ourselves what are the properties of the probability mass function. It has to be non-negative because it's a probability. It sums up to 1 over all the possible values of the discrete random variable over all the range. And for any subset of the range, these are the possible values of the discrete random variable, we can compute the probability that the random variable belongs to that subset by just summing over the relevant values. Okay, these are the three main properties of a probability mass function. Let's take a look at an example. So here we're modeling the goal difference between two teams that are playing a soccer game. In the notes, the two teams are Atlético de Madrid and Barcelona. So this means that I think Barcelona wins by 1, or they lose by 1, they win by 2, they lose by 2, or 0 means that there's a tie. Okay? And we have, used a bunch of data to determine that those are the probabilities. So this is the probability mass function of the goal difference. Now, what is the probability that the goal differences in the set -2, 2, so that it's -2 or 2. What do? We sum the values of the probability mass function over that set. In this case, -2, 0.1, 2, 0.1, so the value should be 0.1 plus 0.1, 0.2. Okay, there you go. What about the probability that the random variable is strictly larger than 1? So those are these two values. The probability mass function is 0.1, 0.05, boom, 0.15. That's what we mean when we say that the probability mass function completely characterizes the behavior of the random variable. If you're interested in, the probability that the random variable does anything, you can compute it from the probability mass function. Okay, so now let's consider the question, what is the distribution of the points gained by each of these soccer teams from that game? If you're not familiar with soccer, let me tell you that usually in most soccer leagues, if you tie a game, you get 1 point. So that's why the number of points is 1 if the goal difference is 0. If you lose a game, you get 0 points. Okay, so here we're looking at it from the perspective of the team that loses if the goal difference is negative. And if you win, you get 3 points. Okay? So that particular team, I think it was Barcelona in the example, unless I'm getting it wrong, will earn 0 points if the goal difference is negative, 1 point if there's a tie, 3 points if the goal difference is positive. But now, what is the distribution? So what is the probability mass function of this new random variable? Well, first we have to ask ourselves, is this a random variable? And this happens very often in probabilistic modeling. You have a random variable, you have an uncertain quantity, and suddenly you're interested in a deterministic function of that uncertain quantity. So A here is our original random variable, but now we have a deterministic function which we're calling h of that random variable. In our example, h is given by that. So now our question is that a random variable? Well, if you think about it, the random variable a takes several possible values, a1, a2, and so on, which means that when we pass it through the deterministic function, this new object is going to take values ha1, ha2, and so on, and it's also going to be uncertain. So intuitively, this kind of should be a random variable. Okay, like if you think about it a little bit more mathematically, the original random variable maps from the sample space to this range a1, a2, and so on. That means that the new random variable maps from the same sample space to this new range ha1, ha2, and so on. So it sounds like this should be a valid random variable. Of course, your friend the mathematician is going to be like, excellent, but there's something missing in the definition. Is this function measurable? Let's take a look at a picture. So remember this picture. Basically, here I'm drawing the sample space, and this random variable has 3 possible values. The original one, okay, the random variable a. It has 3 possible values, a1, a2, and a3. And here what we've drawn is the events that contain all the outcomes that are mapped by a to those 3 values. And if you remember, what do we mean by measurable? We just mean that each of these guys is assigned a probability in the probability space, so that then we can actually define that probability and we have the probability mass function of the random variable. But now what we're saying is that there's this function h, okay, h. So just to be clear, all of these guys are a. So there's this function h that maps the points to these new points. So let's say that h maps a1 and a2 to b1 and a3 to b2. If you realize, now we have a new random variable where a1 and a2 have been merged. So this whole set of outcomes maps to B1, and this set of outcomes maps to B2. Okay, this is getting a bit messy, but we can call this a random variable B. Maybe I should have written them in the same color, but like, you know, B is mapping certain events to B1 and to B2. And if the way this is constructed, those events are always going to be unions of the original events A1, A2, A3. Here I mean big A1, big A2, and big A3. They're always going to be unions. Why? Because we're going through these intermediate points. Okay, I hope the picture is kind of clear. So this means that these new sets, we can call this set B1 and this other set B2. Those guys are going to be unions of the original sets A1, A2, A3. So in particular, by the rules of probability spaces, they have to be in the collection and they have to be assigned a probability. So we're good. This is going to be a valid random variable. Okay, so we need the probability of B equal to every possible value to be well defined, and the possible values again are those that we obtain by mapping the range of the original random variable through the deterministic function h. We need those guys to exist, so we define them. Okay, these are the original the original events B1, B2, and so on. And it turns out that you can write them as a union of these sets, of these events, which are the AIs. And we already saw that for the original random variable and when I say A, here I'm using A for way too many things, but the squiggly line A, for that guy to be a valid random variable, then these events must be assigned a probability, which means that their union is also assigned a probability, which means that these guys are also assigned a probability. So here, even though I said at the beginning of the video that we wouldn't be delving into the mathematical definition of the random variables, it turns out that we needed to do it for a bit. And this is a good example of how typically we don't care about the mathematical definition in terms of probability spaces, but when we define a new object, we often have to go there and see if it makes sense, right? If it's mathematically compatible with everything else. And that's what we're doing now for the definition of a function of a random variable. And that's why it's important to kind of be aware of these underlying probability spaces, even though we end up ignoring them most of the time. All right, but our conclusion is that yes, if you have a deterministic function of a discrete random variable, it is going to be a valid random variable. But now we want to use that random variable. So how do we compute its probability mass function, which is its user interface, what we really, at the end of the day, use to manipulate it? Well, it's kind of quite easy when we look at the definition. So remember that the probability mass function at a certain value is just the probability that the random variable is equal to that value. But now we're assuming, by the way, I should have said this, that we know the probability mass function of A. Okay, we have this random variable that we have characterized from data or whatever. Now we want to derive the probability mass function of this new random variable. So we know the probability mass function of A, and as I often tell you, when you're doing derivations, you need to take into account what you know, and you need to try to get there. So in this case, we know the probability mass function of A. Let's try to express this in terms of A. And we know that B is equal to HA, right? So now we have the probability that HA is equal to B. In our picture, I'm going to go back to our picture, even though that will require, okay. So in our picture, we're saying what's the probability? Maybe let me use a different color. I'm running out of colors here. What's the probability that I end up in B1? What do I need to do? I need to see what values map to B1, in this case A1 and A2, and I'm just going to add the probabilities of A1 and A2. If you want to be very mathematical, you see that this green event is a union of A1 and A2, and these guys are disjoint, right? So I can add up their probabilities if you want to be super mathematical about it and give like a very formal proof. But maybe more intuitively, what's the probability that B is equal to this little b? Well, you take all the values that map there, all the values that map to that particular value, and you add up their probabilities, because, you know, by the properties of probability mass functions, that's going to give you the probability that HA is equal to B. Okay, hopefully that makes sense. It's very intuitive. And to see how intuitive it is, let's take a look at the example where we want to derive the probability mass function of the points gained by the soccer team. So here we have the original probability mass function of G. We want the probability mass function of X. So what do? We see what are the possible values that X can take, the range of X, 0, 1, and 3. All right, so for 0, that means that you lose. So -2 and -1. So we have to add up 0.1 and 0.3. That's going to be, 0.1 and 0.2. That's going to be 0.3. A tie, which gives you 1 point, is when there's a 0 goal difference. That's going to be 0.3. And now when do we win? When we have a positive goal difference, and that's going to add up to 0.4. How did I know so quickly that this adds up to 0.4? Well, this has to be a valid probability mass function. So the probabilities have to be non-negative, which they are, but they also need to add up to 1. And we can check that they do add up to 1. And when you derive a probability mass function in the homework, but also like in real life, you need to check that it adds up to 1, because if it doesn't, then you have a problem. Okay, and this is how the new probability mass function looks like. Again, it's a valid probability mass function. It sums up to 1. All right, so in practice, because the probability mass function is the user interface of a discrete random variable, that's what we're going to estimate from data. How do we estimate it from data? So let's think about a very concrete example. Imagine that you're interested in estimating the value of the probability mass function at 1. And you observe these data points. By definition, what is the probability mass function at 1? It's the probability that the random variable equals 1. So if you're seeing these guys, a very reasonable estimate for that probability is the empirical probability that the random variable equals 1, which we obtain by just computing the fraction of 1s. In this case, 4/6. So the probability would be estimated to be 2/3. And it's as simple as that. The empirical PMF estimator for the probability mass function of a discrete random variable does exactly what we just did. Imagine that you have n data points with values in a discrete set A, which is going to be the range of the random variable that we're going to use to model this quantity. The empirical probability mass function of the data at A is the fraction of points that end up in A. This is an indicator variable that tells you that is equal to 1 if the point is in A and 0 otherwise. So this is just the number of points that are in A divided by the total number of points. It's as simple as that. Here, by the way, we are in the realm of statistics. We're looking at how to extract these probabilistic quantities from data. Okay, this is no longer probability theory. But once you have estimated the probability mass function, then you can manipulate it with the rules of probability theory. And because of that, you have to ask yourself, is this a valid probability mass function always? Like what I got from this statistical procedure, is it fine? Is it a valid probability mass function? So now you tell me, is it non-negative? Yes, right? Because it's, if you look at the definition, we're dividing two non-negative numbers. We're always going to have a number n that is above 0, that is greater than 0. So yes, it's definitely non-negative. We also need it to add up to 1. Okay, does it sum up to 1? Well, we plug in the definition, and now what we notice is that each data point has to be at least in one of the, to be equal to one of the values in A, just by definition, because that contains all the possible values. So that means that when we sum over all the data points, this quantity is just equal to 1. So this whole thing is just going to be equal to 1 over n. We added, actually, that's kind of funny because that's not true. Because I thought we had interchanged the sums. So that's what we need to do. We have to interchange the sums. Otherwise, what I was saying makes no sense at all. So what I was saying is here, if we sum this indicator function over the whole range of the random variable or the possible values that it can take, it has to be 1 for exactly one of them, right? Because the data point can only be equal to one of those values. So the sum over all the possible values, this is always 1, which means that then when we sum over all of the data points, that is equal to n. So divided by n, it's equal to 1. Okay, sorry about it. I got confused about the two sums. Okay, so yes, it is a valid PMF. Does that mean that it's the true PMF? So imagine that indeed, you're generating these samples or this data from a PMF. Are you going to see the right PMF? Or before that, actually, what I'm talking about is the next slide. Before that, let me say that at the end of the day, if you come at this from like common sense without knowing any probability theory, how are we building the empirical PMF? We're taking a histogram. So this is a histogram of some die rolls that I talked about in the video on estimating probabilities from data. Okay, this is a histogram of die rolls. We normalize, essentially what we're doing is we're counting how many times we see each of the possible values from 1 to 6, and then we're dividing by the number of points. So the empirical PMF is just a normalized histogram. You probably have come across histograms before. You can also think of the empirical PMF like that, a normalized histogram, so that it's a valid probability mass function. Okay, so now let me reconnect with what I was going to talk about, which is what if, sorry, not what if, but like we have shown that this empirical probability mass function is a valid probability mass function. But is it correct? Like, is it accurate? What do I mean by that? Imagine that you are rolling a fair die, which means that the probability of each of the values truly is 1 over 6. But you get to see a finite number of rolls, for example, 60. Are you actually going to be able to estimate this PMF exactly? No, we already talked about this, right? When you're computing empirical probabilities, they're not going to be exact because of the fact that you have limited data. So this is what you would see for some 60 rolls. If you repeat the experiment, you would see something different. And if you repeat the experiment, you would see something different. So you need to be aware of that. When you're estimating a probability mass function from data, the estimate is not going to be accurate, even if there's like a true probability mass function underlying the data, which is not necessarily the case. Connected to that, let's see what happens when we compute the empirical probability mass function from real data. So now we're trying to model streaks of consecutive free throws shot by Kevin Durant in the NBA. We have 377 streaks from a total of 3,000 free throws. What do I mean by a streak? It's just the number of consecutive free throws that he makes before he misses. So our data looks like this. Here he made 2 free throws and then missed. He made 4 free throws in a row and then missed. Then he made 17 and then missed, and so on and so forth. How are we going to compute the empirical PMF of this data? Well, let's take an example. There are 42 streaks of length 2 in the data set. What is the probability that a streak is going to have length 2? 42 divided by the total number of streaks. As simple as that. That's the empirical PMF. If we plot it, this is what it looks like. But now you have to ask yourself, how good is this empirical PMF? How does it capture the probability that Kevin Durant is actually going to shoot a streak of a certain length? The overall shape makes sense. It's normal for the probability of shorter streaks to be higher than those of longer streaks. But there's some strange things, right? So, for example, it's weird that this probability is higher than this probability because it's more difficult to have a longer streak, or you would think, at least even from the overall shape of the PMF. So it's likely that this is just noise. That's what I would think, at least. There's nothing special about the number 9 with respect to the number 7. There's no reason why the probability of 9 should be higher. In the same spirit, all of these guys are zeros, but suddenly this guy is non-zero and this guy is non-zero. Is there something very special about the number 52 as opposed to 50? Do we really believe that the probability of making 52, which by the way is insane, but anyways, making 52 free throws in a row in an NBA game, right? Like, this is not in my backyard. Do we think that if the probability of making 52 free throws is non-zero, the probability of 50 is zero? Like, does that make sense? Probably not, right? What is happening? We only have 300 and something streaks. The probability of making 50 something free throws in a row is relatively low, so we just don't get to observe it often enough to be able to estimate all of these probabilities precisely. And that's a limitation of the empirical probability mass function. It's a non-parametric estimator. We're going to talk about parametric estimators in the next video. And therefore, it tends to be noisy if you don't have enough data. All right, so what have we learned? We have learned the properties of the PMF, and we have learned how to derive the PMF of a function of a random variable, and we have learned how to estimate the PMF from data. And that's all I got. Thank you very much.